Alrighty, and we are back. So this is going to be kind of a long one, so I hope I can get through it all today. So we're going to jump straight into the homework, which I hope you enjoyed. And so we're going to start with number 18. And number 18 was f of x is equal to negative x cubed plus 6x squared minus 5. Don't want to do plus 5. So that is the function. We're going to jump straight into knocking it out so we can graph it by hand. First things first, are there any discontinuities? Absolutely not. Why? Because this is a polynomial. Polynomials do not have discontinuity. So we can skip that, go straight to step 2, and this is where we're looking at our critical numbers. Okay, and for the critical numbers we need f prime of x. So f prime of x is going to equal what? Well, negative 3x squared plus 12x is what we're going to get for that. And so part A, are there any discontinuities? No, that's still a polynomial, so there are no discontinuities. That's nice. Part B, then we need to set f prime of x equal to 0, which implies that negative 3x squared plus 12x equals 0. And so I'm going to factor out a negative 3x. What I'm going to be left with x minus 4 equals 0, which means I'm going to have x equals 0 as a critical number and x equals 4. Okay? So now that I have that, I can go straight into my chart, my f prime chart. And let's see, let's make it over here. We'll have a little more room. Alrighty, so I've got x equals 0 and x equals 4. All right, I need some test values for my f prime. Let's see. How about x equals negative 1 for over here? So that means f prime of negative 1 is equal to, well, if I plug a negative 1 in here, it gets squared, becomes positive, times negative 3. So it's going to be negative 3, and then minus 12. So that's definitely negative, which means that I'm going to have a decreasing interval right there. And then a value between negative 1 and 4. How about not negative 1, 4, between 0 and 4. How about x equals positive 1 now? So f equals positive 1, I'm going to have f prime of 1 equals, well, if I plug 1 in, I get negative 3 plus 12. That is definitely positive. So I have an increasing interval right there. Slope is up. Finally, I need a value greater than 4, maybe x equals 10. F prime of 10 is going to be negative 300 plus 120, definitely negative. So it is going down. That means at x equals 0, I have a min, and at x equals 4, I have a max. Okay, not too bad so far. So we're going to clear this and go to the next screen. So step 4, now I need to worry about my inflection points. So what do I do for them? Well, I need my f double prime of x for this, and that's going to be, when I take the derivative, negative 6x plus 12. And there you have it. So, part A, are there any discontinuities? No, there are no discontinuities. Like I said, I've only seen that a few places, so maybe once. I don't even know why I'm putting time into it. But that's okay. Step 2, f double prime of x equals 0. Alrighty, so that implies that negative 6x plus 12 equals 0. And if I can just kind of solve for this, imagine moving the 12 over, get negative 12 divided by negative 6, x equals 2. That's going to be my inflection point. So I've got that. So step 5, I'm going to do the f double prime chart. So I'm going to just put it over here. How about right there? I've got x equals 2. Okay, and so I need a test value less than 2. How about 0? Yeah, that works for me. X equals 0. F double prime of 0 is going to be, well, 0 plus 12. That's definitely positive. So I have concave up for that interval. And then over here at test value greater than x equals 2, how about x equals, I don't know, 10? So f double prime of 10 is going to be negative 60 plus 12, definitely negative, which is concave down. Alrighty? So now I can do my y values. So the y values are going to be, first I'm going to find the y values for the critical numbers. And so those values were at x equals 0 and x equals 4. So for x equals 0, I plug that into my original function. My original function was f of x equals negative x cubed plus 6x squared minus 5. So for f at 0, I'm going to get 0, 0, negative 5. That's not too bad. So I've got a point at 0, negative 5. Alrighty, now I go to the next one, f of 4, and that's going to be negative 64 plus 96 minus 5. So negative 69 plus 96 is positive 27. So 427. And last, I've got my inflection point. So that occurred at x equals 2. So f of 2 is going to equal, well, negative 8 plus 12 minus 5, negative 1. This is going to be 2, negative 1. Okay, so now I have my 3 points and I can graph them out. So I'm going to clear this and make a graph. Let's see. Graph is going to look something like this. And I've got maybe 1, 2, 1, 2, 3, 4, 5, 1, 2. Oh wait, I can't do that on this because I just remember I have large values. So we're just going to put little tick marks for those values so that I don't have to draw 27 of them. So 27 up here, and how about negative 5 down here? That works for me. And that would make this one maybe negative 1. All right. So 3 points are going to be at 0, negative 5. That's where I said I had a min. And then I've got 427. So 1, 2, 3, 4. Up here, I've got a point. That's going to be my max. And then I've got an inflection point at 2, negative 1. So right here is an inflection point. Alrighty. So if I look at my chart, I had decreasing, increasing, decreasing. And I also had concave up and concave down. Well, that kind of makes the chart for me. I can picture this. So it's going to be something like this. Min, switches, assuming I can draw, and it does that. So this is always assuming I can draw, which I can't. Something like that, maybe. But the inflection point switch happened right here. Something like that. So it's concave up, and I should actually probably extend that out just a little bit, but it's mostly accurate. It's a little bit strange because of the way that I had it drawn. So right here, here's the point. It needs to come up and switch like that. So it's kind of a strange, it's because I squished the graph, honestly. If I had done this out, it would be a lot easier to see, but that's the basic shape of what we have, and this is perfectly fine when you're actually doing this for your take-home. This is it. You don't have to get more accurate than this at all. This works absolutely fine. So hopefully this will go well, but I was hoping to spend just a little bit of time talking about this problem in a slightly different form. So has anyone noticed that when we are graphing these things, we first make our f prime chart, and that tells us where we have, in this case, we had decreasing, increasing, decreasing, right, to either side of these. And then I make the f double prime chart, and I have concave up, concave down. The concave up and the concave down tell me what these critical numbers are without even needing the slopes. So if I had not filled in the F prime chart at all, if I just found the critical numbers and then went to the F double prime chart, I would have had the following information. I would have had that the critical numbers were located at x equals 0 and x equals 4. And I would have had from my F double prime chart that to the left of x equals 2, I had concave up, and to the right, I had concave down. That means that this value of 0 has to be a min, and this value at 4 has to be a max. So technically, just by doing the second derivative test, we can fill out whether or not our horizontal slopes are mins or maxes. And you can totally do that. That's 100% fine, but it's a built-in check to make sure you've been doing your derivatives right. So I highly recommend you keep doing the F prime chart and the F double prime chart, especially since this is take home, you're not going to be concerned with time as much, just so that you get a sanity check. Because if you get something that says that for my double prime, I should have concave up, then concave down, but on my F prime, I wound up with something that was increasing, decreasing, increasing. It's a conflict. Something has gone wrong. Conversely, you can always just graph it and know when something has gone off the rails. But if you didn't have the ability to graph using F prime chart and F double prime chart to kind of corroborate each other's information, it's a smart move. But I just wanted to point out that technically you don't need to know where they're increasing and decreasing as long as you have the concavity information. That right there will be plenty in order to graph these things. Just something to think about. Alrighty, so now let's clear this and move on to the next one. Okay, let's see. So for the next one we had 32. And 32 was f of x equals x plus 2 cosine x. I know a lot of y'all love trig functions, and this is 0 to 2 pi. Okay, that's the domain that we're going to have for our x values. First things first, are there any discontinuities? No, absolutely not. X is a polynomial, cosine x is always continuous, therefore continuous plus continuous is continuous, so no discontinuities. Okay, step 2. Well, we need to get our critical numbers. And these are going to take a little bit of thinking. They occur at f prime of x, so f prime of x is going to equal derivative of x is 1, derivative of 2 cosine x is going to be negative 2 sine x. Okay? Now, are there any discontinuities? No, again, continuous, that's polynomial, that's sine function, adding or subtracting continuous functions is still continuous, therefore we have no discontinuities. Okay? Part B, f prime of x equals 0. Well, that implies that 1 minus 2 sine x equals 0, or negative 2 sine x equals negative 1, or sine x equals 1/2. Alrighty, time to consult our unit circle. I know some of y'all just love the unit circle. So, is the sine value the x or y coordinate? Sine values are always the y coordinate, so we're going to look for the y coordinates on the unit circle that have a value of positive 1/2, and that's going to occur right here because this is at pi over 6. We have root 3 over 2 comma 1/2, so there's our y value equals 1/2. And then right over here at 5 pi over 6, we also have a y value of 1/2, but now it's negative root 3 over 2, 1/2. Okay? So those are going to be our two values. So x is equal to pi over 6, and x is equal to 5 pi over 6. Okay, so now that we have our critical numbers, we can make our f prime chart. So step 3, the f prime chart. We're going to have our two locations. We're going to have x equals pi over 6 and x equals 5 pi over 6. So now that we've got that, we can start looking for our test values. Test values that I'm going to need, well, I need something that is going to be less than pi over 6. And since 0 was included, I'm just going to pick 0. So how about x equals 0? So f prime of 0 is going to be, well, what is my f prime? 1 minus 2 sine x. So this is going to be 1 minus 2 times, what is sine of 0? Well, sine of 0 is the y value right here, and that value is 0. So that's going to be a 0, which is going to leave 1, which is positive. So we're going to have increasing on that interval. Now I need a value between pi over 6 and 5 pi over 6. So somewhere in here, I like this one an awful lot. This is going to be pi over 2. So let's do x equals pi over 2. And when we do that, we're going to get f prime of pi over 2. And so I'm going to get 1 minus 2 times the sine of pi over 2. Well, the sine of pi over 2 is the y value at pi over 2, and that is a positive 1. So this becomes 1 minus 2 times 1, which is negative. So this is negative, which means we have decreasing. Okay, finally, a value greater than 5 pi over 6. How about pi right there? So we'll just do pi. So f, let me write that down, x equals pi. F prime of pi is going to equal 1 minus 2 times the sine of pi. Well, again, it's the y value right here, which is 0, which is just 1, so that's positive, which means we have increasing. So we have a max at pi over 6 and a min at 5 pi over 6. Alrighty? So let's clear the board and move on to our not critical, but our inflection points. So step 4, inflection points. Okay, well, for inflection points, we need f double prime of x. And since f prime of x was equal to 1 minus 2 sine x, f double prime is going to be, well, the 1's going to become a 0, and I'm going to have negative 2 cosine x. That's all my f double prime is. So, any discontinuities? No, no discontinuities. Cosine is always continuous. Part B, f double prime equals x, 0. Well, that implies that negative 2 cosine x equals 0. Divide both sides by negative 2. Cosine x equals 0. So we're going to go back to our unit circle, and cosine is the x value. So when are the x values equal to 0 on this unit circle? Well, they're right there at pi over 2, and right here at 3 pi over 2. Alrighty, so my x values for my inflection points are at pi over 2 and 3 pi over 2. Okay, so now I can do my f double prime chart. So step 5, I've got f double prime chart. So here we go. I'm going to have two locations, x equals pi over 2 and x equals 3 pi over 2. Alrighty, so test value less than pi over 2. How about 0? Yeah, that works for me. X equals 0, we're going to get f double prime of 0, which is, if I look at my f double prime, I've got negative 2 times cosine of 0. Alrighty, cosine of 0. Well, cosine is the x value, and here's the 0 for the radian measure, so I'm going to have negative 2 times 1, which is going to be negative. So it's going to be concave down. Alrighty, now a test value between pi over 2 and 3 pi over 2. How about pi right there? Okay, so x equals pi. F double prime of pi equals, Well, again, negative 2 times cosine of pi. Well, cosine of pi, now what is the x value? It's negative 1. So negative 2 times negative 1 is positive. So I have concave up. And finally, a value greater than 3 pi over 2. How about 2 pi? It's the same as x equals 0, so I don't even have to do anything. I can just say f double prime 2 pi is going to be negative, which is going to be concave down. All right. So let us, now the last part, and it's the weirdest part, let's do the y values. So clear this and do some y values. So here we go. Y values, step 6. So I've got my critical numbers first. Okay, so that was x equals pi over 6 and x equals 5 pi over 6. I think that was right. Okay, so f of pi over 6. Well, what was f? F was, let's see if we look back, f of x equals x plus 2 cosine x. Okay, so this is going to equal pi over 6 plus 2 times, what was the cosine of pi over 6? Well, that was root 3 over 2. So I'm going to get pi over 6 plus root 3. And that is approximately, if I do it out, 2.2, roughly. Alrighty? And how did I know that? I did it beforehand. Pi over 6 is going to be 0.5 something, and then this is square root of 3 is 1.7 something. So 0.5 and 1.7, about 2.2, so it makes sense. F of 5 pi over 6 is going to be 5 pi over 6 plus 2 times, well, now we've got negative root 3 over 2, right? So this is 5 pi over 6 minus root 3. And 5 pi over 6 is going to be about 2.5, something like that. And then this is root 3 is 1.7, so maybe 0.8-ish. So 0.8. It doesn't have to be exact. It's just an approximation. So now I can move to the inflection points. So the inflection points, I don't know why I did that. Inflection points they were at x equals pi over 2 and x equals 3 pi over 2, right? So f of pi over 2 is going to equal pi over 2 plus 2 times, well, what is cosine of pi over 2? Well, that is 0. So this is just pi over 2, and pi over 2 is approximately, what is it, 1.57, something like that. And then f of 3 pi over 2 is going to be 3 pi over 2 plus 2 times, well, 0 again. So it's just 3 pi over 2, which is approximately 3 of those, so 4.7-ish, something like that. Okay, so now I can graph all this. So keep all these values in mind as we graph it. So I'm going to clear the screen. I know I hate to, but I need the room so this can look even halfway decent. So here we go. We're going to put 2 pi here, pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. Okay? Now, the values are going to go up to 4.7-ish, so I'm going to go ahead and make this 5 and try to divide that into 5 pieces. 2, 3. Okay, so first one is going to be at pi over 6 and about 2.2, so pi over 6, 2.2, and that is, I don't remember what that was. What was that? That one was a max. Yeah. And then I've got, for the next one, 5 pi over 6 and about 0.8, so somewhere around here. And I should probably label these. This is pi over 6, and then the value was around 2.2, 2.2, and this is 5 pi over 6 over 6, and about 0.8, something like that. It doesn't have to be perfect, which my pi symbol is definitely not perfect. Okay, so there's my 6. Here we go. Those are the two critical numbers. Now the inflection points, we had pi over 2 and pi over 2, and we said that was right about here. That's an inflection point, and the other inflection point is at 3 pi over 2 and right about up here. Okay, so what does this look like? Well, max, min, I have increasing, decreasing, increasing behavior, and that's good. I have concave down, concave up, concave down over here. So this is going to be a little bit tricky to draw, but I think we can do it. This one is no problem. This makes perfect sense. It's just a curve that looks something like this. But now this one is concave up until I hit this point, and then it starts to go concave down. So I've got to do a long concave up, concave up, concave up, concave up, switch, concave down, something like that. And there you have it. That's what the graph looks like. If you actually look at it in Desmos, you will see that this is actually the y equals x graph with the sine function kind of wiggling along like that. And that's it. I don't know what that was. My pen must have slipped. Alrighty. I hope you enjoyed that one. Now we can tackle the very last one, which is much, much more complicated while also being way simpler. So here we go. Let's clear the board and try it and see what we get. So for the very last one, here we go. We've got, let's see, 42. F of x equals 9x minus 1 over x plus 5. Okay. First off, step 1, discontinuities. Well, absolutely. When x is negative 5, the bottom goes to 0. So at x equals 5. Is that a whole or a vertical asymptote? Well, that's a whole. Because if I plug negative 5 up here, I do not get 0 for the top. So vertical asymptote, which is good. Okay. Now, step 2. I need the critical numbers. And that occurs when I have my f prime of x. So f prime of x is going to be bottom. So x plus 5 times derivative of the top, 9, minus the top, 9x minus 1 times derivative of the bottom, 1, over the bottom squared, so x plus 5 quantity squared. So we're going to wind up with 9x plus 45 minus 9x plus 1 over x plus 5 squared. That's going to give me 46 over x plus 5 quantity squared. Alrighty, so part A, discontinuities. Well, yeah, we already know about it. It said x equals negative 5. That's supposed to be negative 5. So it's still the same. X equals negative 5 will make that go to 0, so we don't have to worry about that. We already know which one is there. So we can skip that and go straight to part B. F prime of x equals 0. Well, that implies that 46 equals 0. Alrighty, what values of x make 46 equal 0? Never. No solution. There are no horizontal slopes. for this one, okay? So now that I know that, I can go from that straight to my chart. Here, I'll put the chart right here. I'll make it fit right there. So the F prime chart. Let's do all these values up. Well, there are no values, so we can skip. Alrighty. So no critical numbers means no F prime chart. All right, let's go straight to step 2. So step 2, let me clear this. Step 4 rather, not step 2, step 4. So step 4, I get the second bit of information I want, and those are going to be the inflection points. And so the inflection points require F double prime. So F double prime of X is going to equal, well, let me do a little work with this F prime of X. So F prime of X was 46 over X plus 5 quantity squared, right? I can actually rewrite this to where I don't have to do a quotient rule, because this is actually 46 times X plus 5 to the negative second power. So I can do my F double prime much, much faster by just doing a power rule. Negative 2 times 46 is negative 92 times X plus 5 I have to subtract 1 from this, so negative third power times the derivative of the interior, 1. So that's all it is. So this becomes negative 92 over X plus 5 quantity cubed. Way faster, right? So I have that. Now, are there any discontinuities? Yes, I already knew about the discontinuity at X equals negative 5. What about part B? F double prime of X equals 0 implies that negative 92 equals 0. Nope. No solution. Well, what does that mean? There are no inflection points either. So, step 5 with the F double prime chart, skip. You don't need it. You can't do anything with it. So, as a slight recap, I have no critical numbers and no inflection points. This is going to be a very weird graph. 6. I need the y values for my critical numbers and inflection points. Skip. There are none, so I can't get y values for them. So now we can go straight to graphing this. Alrighty? So let me clear and graph this. Let's make a nice graph. Something like this. 1, 2, 3, 4, 5. Okay? I have a vertical asymptote at x equals negative 5. And then I have no other information. I have no critical numbers. I have no inflection points. I need something to be able to take a stab at this. So what I'm going to do is, even though I don't have critical numbers, I'm going to see what the slope is on either side of this x equals negative 5, the vertical asymptote. So I want my f prime equation. My f prime of x equation was, what was it, 46 over x plus 5 quantity squared. Alrighty, so I want to plug a test value in that is less than negative 5, maybe negative 10, doesn't matter, because whatever value I put in here is going to get squared. So the bottom is always going to be positive no matter what I put in. Top is always positive. That means I have positive slope on either side of this vertical asymptote. So that tells me that I'll have something that looks like this. I have no critical numbers, which means no horizontal slopes. I have no inflection points, which means no change in concavity. So the only way I can have a upslope, positive slope is if I do something like this. I'm going to go like that and like this. In order to not have anything, well, I guess you could do that. I'm just going to leave it like that right now. Stop talking. So I don't want to spoil anything. What I really need for this graph is I need to know where these things are located, where I have this like thing that they are approaching from the top and the bottom. That way I can orient them into space and everything's fine. So we need one final bit of information before we can graph graphs by hand. That final bit of information is we need to know where horizontal asymptotes lie. And what is a horizontal asymptote? Well, it's kind of neat. Let's think about what a vertical asymptote is. A vertical asymptote, as my x value approaches it, the y value gets large without bound. It heads up to a positive infinity, heads down to a negative infinity, right? Same type of thing for a horizontal asymptote. A horizontal asymptote would be a line that, as I approached it, getting closer and closer and closer, and for the x values, let me rephrase that. As I approached it along the y, the x values get large without bound or small without bound. In other words, this thing is heading out to a positive infinity. And this one over here, if I curved it down a little bit better, is heading to a negative infinity. But they're never going to cross this thing. Okay, at least for this type of graph, that's what it's going to look like. So I need to be able to find out where my horizontal asymptotes lie on these graphs. And that is the very next section, which is limits at infinity. So we are all set now to start in on 3.5 and actually figure out where the horizontal asymptote has to lie in that original function that we just did. Alrighty, well, I will clear this and we will start in on that section. So clear, and here we go. Okay, so let's see here. Let's do something really odd. So this is starting 3.5. Let's say I have f of x equal to, I'm going to bump up the thing so it gets a little more ink on the page. So, oh, that looks so much better. 3x squared over x squared plus 1. Okay? Now, this is really close to 3x squared over x squared. So I'm going to start looking at this function and then move to this function. So first off, let's say that I have a chart for this function where I have an x value and then I have an f of x value. Okay? So I'm just going to put values in and you can tell me what, if I have an x, what I get for my y or my f of x. Alrighty, so x equals 1. What is f of x? Well, f of x would be 3 times 1 divided by 1, which is going to be 3. Alrighty, what about x equals 2? Well, that's 3 times 4 divided by 4. Well, so that's just 3. What x equals 3? 3 times 9 divided by 9. Well, that's 3. What about 1,000? 3 times a million divided by a million? 3. Alrighty, you see a pattern? I sure do. Of course, we already knew that that's what we would get because we could simplify this by canceling the x squares and we would just have 3. That's not important. What's important is I am always going to be settling on the value 3. Okay? Now, all I'm going to do is take the exact same function and add 1 to the denominator. Alrighty? So here we go. Let's make another chart. And let's start filling it out. Now, if I do 1 here, I get 3 times 1 over 1 plus 1. So 3 over 2, which is 1.5. Definitely not 3. Okay. Let's go out a little bit further. Let's go to 10, see what happens. Well, I'm going to get 3 times 100 divided by 101. Well, that, it turns out, is 2.97. Okay. Now, let's go out to 1,000. 3 times a million divided by a million plus 1, so 1,000,001, is going to be 2.999997. See a pattern? Well, definitely. What happens is, at the very beginning, when I have values that are small, x values that are small, there's a difference between the f of x is 3x squared over x squared and 3x squared over x squared plus 1. There's quite a bit of a difference. But as I head out to x values that are getting larger and larger and larger, I'm going to get closer and closer and closer to 3, because this 1 doesn't really matter that much once the x values get large enough. Okay? So as I head out to positive infinity, guess what my value that I'm approaching is going to be? 3. So in calculus speak, since we know calculus and we can actually do this now, I could say something like the limit as x approaches infinity equals, drum roll, race, super fast, 3. What in the world? I'm a fuzzy. How'd I get a fuzzy? That's weird. That just totally stole my thunder. Bah. 3. Oh, apparently the option is to have a chalk for the mispress the button, I guess. So anyways, that's not important. The limit as I go out to infinity is going to be 3, because it's going to get closer and closer and closer and closer without any kind of bound to 3. I can put as many 9s after the 2 as I want by just getting further and further and further out towards infinity. Okay? Now, let's look at what's really happening with this. Okay? So what I'm going to do is take this function right here, and we're going to run it through the ringer. F of x equals 3x squared over x squared plus 1. Okay? I want to know what the limit, I'll put it up here, as x approaches infinity of this expression is. X squared plus 1. Okay? What is that limit going to be? One way to figure that out, and this is a huge trick, I use this trick all the time, so this is gold level trick, I don't know. It is a trick for calc, for limits, and I'd say it's a trick, it's a technique. I probably should call it that. That sounds a little bit better. The way I can tell what the end behavior is going to be like as I head out towards infinity is by simplifying things to where my x's kind of vanished. They are no longer part of the equation. Or let me rephrase that. To find the end behavior, an easy way to do that would be to simplify things to where I didn't have to worry about the x's. I just had to worry about a value of some sort. Okay? So the way you can do that is to take every single term and divide it by the highest power of your variable. Just like this. Okay? So you divide every term by the highest power variable. Okay? We had an x squared as our highest power, so we divide every single one of the terms by that x squared. Well, let's see what happens when we do that. So I'm going to clear this and start back over. I have the limit as x goes to infinity of 3x squared over x squared plus 1. And I said that I divide every term by x squared, so that becomes 3x squared divided by x squared over x squared divided by x squared plus 1 over x squared. Okay? So 3x squared over x squared becomes 3. X squared over x squared becomes 1. And then I have 1 over x squared. Now that I have simplified everything by dividing it by the highest powered variable, I can now take my limit. So I'm looking at the limit as x goes to infinity. What happens to 1 over x squared as x goes to infinity? Well, we already know, I think from a long time ago, that if I have a limit as x goes to infinity of something that is a constant on top and an x on the bottom is getting large without bound. The top is a constant. It stays the same. So I'm dividing this constant by 10, 100, 10 billion, 100 trillion, 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 et cetera, et cetera. That's not even touching the first step of infinity. So what's happening is this whole thing is going to 0. That's what's going to happen to this term. I have a constant divided by x squared. X squared is going to infinity. This term is going to 0. So this is actually 3 over 1, which is 3. That is the actual behavior as I head out to positive infinity. My f of x is going to equal 3. Alrighty? So that's it. That's all you have to do. But why on earth are we doing this in the first place? We started off with a purpose, a mission. We wanted to find where the horizontal asymptotes were located. Well, what do horizontal asymptotes represent? They represent the behavior of the function as it heads out to positive and negative infinity. They are where the value at which the function will never cross. It'll approach it super closely, but it will never quite make it. So, if you will allow me, let's go back to the example that we had from homework. I'm going to clear all of this so we have a nice clear page. So here we go. Number 42 from the homework was f of x equals 9x minus 1 over x plus 5. Okay? Now, I want to know, are there any horizontal asymptotes? So what I do is I look at the limit as x goes to infinity. Well, when I want to do that, the easiest way to figure that out is to divide every single term by the highest power, x. In that case, it's just x. So I'm going to have 9x over x minus 1 over x over x plus 5 over x. That's going to give me the limit as x goes to infinity of 9 minus 1 over x over 1 plus 5 over x. Okay? These are going to go to 0 when I apply the limit. What am I going to be left with? I'm going to be left with 9 over 1, which is 9. That is where I have my horizontal asymptote. Ha! That is right where it's located. So, I now have a little bit more of information. I have that I had a vertical asymptote, I had a VA at x equals negative 5, and now I've got a horizontal asymptote at x equals 9. So, if I do this out, I'm going to say x equals 5 is right about here, so, or negative 5 rather, and maybe 9 is right here. Don't want to go too high, so, okay. Now, all I know is that the slopes are positive. They're going this way and going this way. They have to. So, because I have this horizontal asymptote and vertical asymptote, I can guarantee the graph looks like this. And on this side, that's the way they always look. Now, with just that single addition of the horizontal asymptote, we can graph 42. That's all it took. Now, the question is, which I know at least a couple of y'all are already thinking of, but wait, we only looked at positive infinity. We only looked this way. How do I know what the behavior is this way? Well, for that, we plug in negative infinity, which in most cases is going to wind up being exactly the same value. So x approaching negative infinity of, if you will allow me, I'm going to go to right here because it's going to be the exact same steps before I plug in the limit. So 9 minus 1 over x over 1 plus 5 over x. If I plug a negative infinity in here, well, it just goes to 0 with a negative number. So it's going to a negative 0, but it's still 0. So it doesn't change. It's still going to have a horizontal asymptote at positive 9. Y equals positive 9. Alrighty. And that is something I also need to say. Horizontal asymptotes occur at y equals, not x equals, of course. So if you have a vertical asymptote and a horizontal asymptote, they always look like this. The graph does these two little wings like that. And you just fill in the boxes depending on if it's a positive slope or a negative slope. A negative slope would have looked something like maybe this. It would have been that, and then this. That would have been a negative if the slopes had been negative. But since they were positive, it's the yellow. And you can actually graph that to verify if you want. Alrighty, so now that we have that, there are a couple of wrinkles to this that we need to go over. So let me clear all this and let's get started on it. So clear this. So let's do some examples. Let's do the limit as x approaches infinity of, here we go, 2x plus 5 over 3x squared plus 1, and then 2x squared plus 5 over 3x squared plus 1, and then finally let's do a third function, 2x cubed plus 5 over 3x squared plus 1. Okay, so let's kind of take this in stages. I'm going to work this one first, straight down, so here we go. I'm going to divide every term by the highest power x, which in this case is going to be x squared, so it's going to be 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. So this is going to simplify to 2 plus 5 over x squared over 3 plus 1 over x squared. Okay, so, oh, sorry, that's 2 over x right here. Don't let me get away with doing silly stuff. 2 over x. Alrighty, so now I'm going to apply my limit as x goes to infinity. When I do that, I'm going to get 0, 0, 0. So I'm going to wind up with 0 over 3, which is 0. Okay, not too surprising, but kind of cool. Now let's work with this one. Divide everything by x squared, so 2x squared over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Simplify, I'm going to get 2 plus 5 over x squared over 3 plus 1 over x squared. When I apply the limit, this is going to go to 0, this is going to go to 0, and so I'm going to wind up with 2/3. Okay, now come over here. This one is a little tricky. Alrighty, so if I divide everything by x cubed, I'm going to get 2x cubed over x cubed plus 5 over x cubed over 3x squared over x cubed plus 1 over x cubed. So I'm going to wind up with 2 plus 5 over x cubed over 3 over x plus 1 over x cubed. Now when I apply the limit, 0, 0, 0. The denominator is heading to 0, but the top is a constant. So this is where we have a situation. The bottom is getting smaller and smaller and smaller without bound. The top is staying as a constant. So this is going to blow up to infinity because the top is a constant. The bottom is heading to 0. This is one of the ones that we did back when we handled limits way back in chapter 1. So if I look at the original expressions, you can kind of see how we arrived at these limits. 2x over 3x squared, those are the terms that are going to matter. This is going to wind up being basically 2 over 2, how to say this, a higher power x is in the denominator, that's a better way of saying it, than in the numerator. So when I take the limit, the denominator is going to get big without bound, which means I'm going to wind up with a 0. Here we have the denominator and the numerator both have the same power, so it's the values that are in front of them that are going to set the limit, so 2 over 3. Here the top has a higher power than the bottom, so when I plug infinity in, it's going to get large without bound and become infinity. So there we have it. That is how that works, and that is good for right now. Since we're running a little bit long, I'm going to go ahead and clear this and give you your homework, and then we will continue next time. So for your homework, tackle, if you will, let me get the right numbers. Okay, so let's go with homework, and this is from section 2.2. Boy, I sure hope we're not in 2. That would be a terrible thing. We'd have our work cut out for us. 3.5. Let's go with try 13, 14, and let me look over here. What was that one that I picked out? It was number 19. So 13 and 14 are just going to be finding the limits. But for 19, actually try to graph that one. Okay, so do the full, 7 steps. And then the very last, step before you graph. So you'll do steps 1 through 6, like normal, where you find the y values and the f prime, f double prime, and all that stuff. This is for 19. But before you go to graph it, for step 7, look for horizontal asymptotes. How do you do that? Look at the limit as x goes to infinity, and you can even, for this one, it's plus or minus infinity, will give you the same value of your function. Okay? When you find your horizontal asymptote, what you're going to wind with is this number 19 is going to wind up very similar to 42, where you're going to have a vertical asymptote and a horizontal asymptote. If the slopes to either side are positive, you're going to wind up with something that looks like this. So that's going to be for a positive slope. So if you have slopes going up like that on either side of your vertical asymptote, if you have negative slopes, then it's going to look something like this. Just like that. So that's what you would get if you had a negative slope. Something look like that on either side. Okay? So try number 19, see how it goes, and we will pick up there. Alrighty, y'all have a good one. Enjoy your Easter holiday, and I will see you in just a few days. Take care. Bye-bye.